Hello guys, so I would like us to look at vectors today. Now a vector is basically a quantity with both magnitude and direction. And usually in writing, you will find that vectors are represented like this with an arrow on top, or written like this, or sometimes just written in bold. So those are the ways you'll find vectors represented in writing. Now, let's take, for example, AB. As you can see, the direction is from AB, and this over the x-axis, we have it moving 4 units, and over the y-axis, we have it moving 3 units. Now, vector AB can be written in its column form, basically by representing the values on the x coordinate and then the value on the y coordinate. So 4, 3. This is referred to the column or the displacement vector. Now, position vector starts from the origin. So if a position of a vector is defined, it's basically from some origin 0. So let's take 0 as our origin, and then we have our y and x coordinates here. So when we look at OA, that is the position vector represented by A, is basically the position from the origin. That's the position vector for OA, which is basically 3, 4, 3 units on the x-axis and then 4 units on the y-axis. And when we look at B, which is basically the position vector of B, as you can see, it's from the origin 0 to B, then it's represented as 5, 2. That's basically the position vector. So the position vector is basically from the origin. So in general, if we have any point x, y, and 0 is the origin, then the position vector of that point P, OP, is basically x, y, because this is how we evaluate vectors. We have OP. Now, vector OP is basically given by P minus O. So if we already know the value for P, which is our x, y, minus O, which is the center, 0, 0, then our answer will just be x, y. Note, if you're evaluating the vector OP, then it is basically P minus O, vector P minus vector O. Okay. Also, if A and B have position vectors A and B with reference to the origin, then basically AB is equal to B minus A. So let's say, for example, we have our OA. So if AB, there are position vectors A and B with reference from the origin. So OA is probably equal to, let's say, some 2, 3 with reference to the origin, and OB is probably equal to some, let's say, 3, 4, such that this is our A and this is our B. So basically AB is given by B minus A. Note that AB is given by B minus A. So in this case here, we will have 3, 4 minus 2, 3. Subtract the upper part, that is 1, 4 minus 3, that is 1. So basically, that's how we go about the position vectors. Now, vector addition and subtraction. So we've already looked at it basically there, but let's just look at it again. Vectors are added by the triangular rule of vector addition. Let's say you have your vector AB, which is A, and then you have your vector BC, which is B. Now, the vector AC is basically given by, if you want to find the vector AC, so let's come here where we've like joined all this up. Vector AC is basically given by AB plus BC, as you can see here. AC is given by AB plus BC. And if AB is A and BC is B, then basically we have our vector AC being equal to A plus B. Okay, so example, we have vector AB being 5, 2, and CD being 2, 3. So what is AB plus CD? So AB plus CD will basically be this vector added to this vector. So we add the upper parts and the lower parts together. So 5 plus 2, 2 plus 3. And if you were to carry out subtraction, the same. This corresponds to this. So we will subtract those two and the lower ones as well. Now, the triangular rule follows from the parallelogram law. Let's say if AB and AD are two non-parallel vectors, so we have AB and AD, which are two non-parallel vectors, AB being equal to A, AD being equal to B, drawn through A. So they are both drawn through A, as we can see. The sum of AB plus AD, if we want to get AB is A, AD is B. So the sum of AB plus AD is basically A plus B. As we can see, sum of AB plus AD is A plus B. Now, that's not it. Let's look at AB plus BC. Sum of AB plus BC. Clearly, this is parallel to this. So BB, this is parallel to this AA. So AB plus BC basically gives us A plus B, as you can see, which is equal to our AC as well. So evaluating AB plus BC is just the same as A getting the value for evaluating AB plus BC, that is A plus B, is just the same as AC. Similarly, evaluating AD plus DC. So clearly, as you can see, AD is B plus A. B plus A is just the same as A plus B because addition is commutative. If you have 3 plus 2, it's just the same as 2 plus 3. Okay. Okay, subtraction can also be performed in a similar manner using the parallelogram law. Let's say we have the value CB. So look at the direction of CB. CB is basically minus B, clearly. CB is basically minus B. So CB is equal to minus BC. Okay, so if we were to carry out AB minus CB, if we were to subtract AB minus BC, that would be the same as AB minus, AB minus CB. AB minus CB would be the same as AB minus CB. We've said that CB is the same as minus BC. As you can see there, CB is like the opposite direction of BC. So AB minus, instead of having CB, we can write minus BC, which is basically the same as AB plus BC. AB plus BC, which is clearly AC. Okay, next, multiplication by a scalar. So a scalar is basically any constant K. So if we have our vector A and we are to multiply vector A with 2, basically we will get 2A in the same direction. We'll get A and another A, so that will basically give us 2. Let's say we take A and now we multiply it by minus 2. We will get minus 2A. So clearly, we will have minus 2A. The direction is going to change. It's no longer going to be on this other direction because of the minus. It's going to be on the opposite direction. So basically, note that negative signs reverse the direction of vectors. Okay. Now let's look at the example we have here. So we have A is equal to I plus 2j plus 3k, and B is equal to 2I plus j. And the value of C is also given. So how do we go about adding and subtracting these vectors? Okay, so if we are to add this, I can just write them in their column form. So A, writing them in their column form without the ijk, so just writing the coefficients, that is 1, 2, 3. These are vectors in 3D, plus this is 2, 1. This position is not there, so I can just write 0. This will give, so you add this to this to this, and this to this. That's how you go about it. So this is 3, this is 3, this is 3. So this is basically the same as 3i plus 3j plus 3k. In a similar manner, if we are to subtract a minus b, so 1, 2, 3, subtract 2, 1, 0. So subtracting that, we will get, so this position to this position, that's -1, 2 minus 1, that is 1, 3 minus 0, that is 3. So this basically gives us minus I plus j plus 3k. And finally, if we have 4a plus 2b, so for a, we will take 4 position, the column vector for a is 1, 2, 3 plus 2. The column vector for b is, so let's see what's the value for b. B is 2, 1, 0. So b is 2, 1, 0. So putting that together, this multiplying by a scalar, you multiply with each term here. So you will have 4, 8, 12 plus multiplying this all through, that will be 4, 2, 0. So putting this together, we will have 8, we will have 10, and we will have 12. We can write this as 8i plus 10j plus 12k. Okay, lastly, 3 into a. So the column vector for a is 1, 2, 3, minus 3 into b. The column vector for b is 2, 1, 0. So putting this together, multiply the scalar throughout the column, we'll have 3, 6, 9, minus multiply the scalar throughout the column, we'll have 6, 3, 0. Okay, subtracting each entity with the corresponding entity on the other column, we have minus 3, 6 minus 3, we have 3, 9 minus 0, we have 9, which is basically the same as minus 3i plus 3j plus 9k. Okay, so that's basically it for addition, subtraction, and multiplication by a scalar. Now, parallel vectors. Now, if two vectors A and B are parallel, then they can be written in this form, like A can be written being equal to some constant K, okay, equal to B. So for example, let's say we have A is 1, 5 and B is 3, 5. Are these two vectors parallel? Let's check. If we take 3, 5, clearly we see that 1 can be written in terms of 3 and vice versa. So 3, 15 is the same as K, 1, 5. Is this true? Is there a number K that if we put here will give us these values? Yes, it's possible. If we take our K to be 3, clearly as we've done here, if we take our K to be 3, then we are going to have it being equal to this other side. So these two vectors are obviously parallel. So as you can see, if we put 3 here, then this is 3 and this is 15. So clearly we can be able to write A with respect to B in terms of having some constant. So we can be able to write in the form A is equal to some KB, where K is a constant. Similarly, if we were to have 1, 5 is equal to K 3 over 5, is there a constant K that if we put here will give us these values of A over here? Yes. So if we choose our K to be a third, let's see how that plays out. If you multiply a third by 3 here, you get 1. If you multiply a third by 15 here, you get 5. So yes, we can be able to write them in the form A is equal to KB or B is equal to KB. Then the vectors are parallel. Now, collinearity. Now, if the vectors are parallel, let's say you have vectors A, B, you can be able to write it with respect to AC, like that. So AB is equal to some constant K is equal to AC, meaning they are parallel. Then, as we can clearly see, they have a common point A. So they are parallel and also have a common point A. Then those vectors are called collinear. Okay, they are not only parallel, but they also have a common point A. Okay, midpoint midpoint of vectors. So if we're given two vectors, A, B, and PQ, then if we need to find the midpoint of, that's like the middle level. So if we have A, B, then like we need to find M, which is the middle point of AB. The middle point of AB is given by us taking this column vectors. So column vectors A plus P divide by 2, and then B plus Q divide by 2. So let's say we have like our AB is 2, 3, and our B is 4, 6. Then the midpoint of this will be, so the midpoint of this will be, our M will be 2 plus 4 over 2, and then 3 plus 6 over 2. That's how we go about getting the midpoint of a vector. So we have an example here. We have our example here. So we have our A 1, 9 and our B 9, 3. So getting the midpoint here, we will take 1 plus 9 divided by 2, as you can see here. 9 plus 3 divided by 2, as you can see here. And this is how we go about getting the midpoint. Okay, fine. Next, let's look at unit vectors. Now, vectors can be written in 2 dimensions, also in 3 dimensions. So let's first of all start with ij. Now, if we have I being equal to 0, 1 and j being equal to 1, 0, these are 2 points on the Cartesian plane. Now, basically, I represented on the x-axis as this, and j is represented on the y-axis as this, as 0.01. Now, unit vectors basically are vectors whose magnitude is 1. So most of the time, when we are representing values, we represent them on the Cartesian plane vectors in terms of I and j. So for example, if we are to represent point P, look at point P here, it is 4 units on the x-axis, so that is 4i, and then 3 units on the y-axis, so that is 3j. So OP, position vector, is given by 4i plus 3j. Now, any vector can be expressed in terms of I and j, any vector, because I basically will represent the value on the x-axis and j, the values on the y-axis. Let's take up, for example, QP. Now, what is vector QP? So this is QP. Now, QP basically is given by, so QP is basically P minus Q, where P is the position vector of P and Q is the position vector of Q, as you can see here. So OP minus OQ. What is OP? OP is the position vector from 0. So OP, as you can see clearly here, we have 4, 3. And what is OQ? From this point here, what is OQ here? So Q is 3 units on the x-axis, so that is 3, 1. So if we write in terms of ij, so that is 4i plus 3j, that is for P, minus OQ, which is 3i plus 4j. So subtracting that, 4i minus 3j will give us I. 3j minus j will give us 2j. So basically, that's the way you express QP. Now, a unit vector, as I've said, is a vector that has magnitude or modulus of 1. Okay, fine. So how do we go about getting modulus? Now, let's say we have a vector OP, which is 4i plus 3j. The modulus of OP is given by squaring the coefficient, that is taking 4 squared plus the coefficient of j, which is 3 squared, and then finding the square root. Now, as I said, that the unit vector has a modulus of 1. So unit vector is I plus j. If you take their coefficients, that is 1 squared plus 1 squared square root, you will clearly get that it is 1. So it has a modulus of 1. So this is how modulus is. It's either called modulus, represented with these 2 lines, or also called magnitude. Okay, fine. Now let's look at unit vector ijk. Now that is in 3D. Now I is basically represented on the x-axis. So if we have x, y, j, so I is basically on the x-axis representing 1, 0, 0, j on the y-axis represented by 0, 1, 1, and k on the z-axis represented by 0, 0, 1 in the k in the z axis. So clearly these are also unit vectors, and as we said, unit vectors, the modulus is 0. So if I have I plus j plus k, the modulus, we take the coefficients, 1 squared plus 1 squared plus 1 squared, square root of this, you get 1. So they have a modulus of 1. Now, evaluating vectors in 3D, so for addition, subtraction, multiplication by a scalar, it will all remain. We do it the same way. And also, if we're evaluating the magnitude, the procedure is the same. So here, if we have OP as I plus 2J plus 3K, then the modulus of OP is given by, so we square the coefficients, and then add, find the square root. 1 squared plus 2 squared plus 3 squared, and then we find the square root. That's how we get the modulus or magnitude of a vector. Now, proportional division of a line. Let's say we have line AB, as we see here, AB, and AP is 3 units, and PB is 3 units. So clearly, AP to PB is 3 to 1. Then we say that P divides AB internally in the ratio 3 to 1. P divides AB internally in the ratio 3 to 1. So clearly AP, as you can see, AP is 3 over the total, which is 4, so 3/4 of AB, and PB is 1 over the total, which is 4, so 1/4 of AB. Okay, now ratio theorem. If a point X divides a given line AB internally in the ratio M to N, then X, which is the position vector of X, is, so if a point, if we have, let's say we have a point X, it divides A, if a point X divides a given line A, B, so it divides our line AB in the ratio, internally in the ratio M to N, then the position vector, so we know the position vector is the one evaluated from the origin. The position vector of X is given by N over M plus N multiplied with A plus, so A, which A is basically the position vector of A, and B the position vector of B, is given by this formula. Now let's take up an example. So this is just a rough sketch. If we had that, then we had our origin somewhere here in order for that to make sense. So our origin 0. Okay, so if this is 0, then this holds. Okay, fine. So now let's take up this question. Now, P and Q are 2 points with position vectors 6i plus 2j minus 4k and 10i plus 10j plus 8k. Find the position vectors of the points A and B if A divides PQ internally in the position 3, 1. Okay, let's have a rough sketch for that. So we have point P, and then we have point Q, and then we are being told A divides, so A divides PQ internally in the ratio 3:1. So we have point A, let's say here, it is dividing PQ in the ratio 3:1. Okay, fine. Let's assume they all have their origin 0 at some point here. Okay, so we have that, we have that, we have that. Okay, so this is the position vector for P. This is the position vector for Q. Okay, and let's call this position vector for A. So find the position vector of the points A and, sorry, find the position vectors of the points A and B. If, so we want to find the position vectors OA and OB. Okay, so let's first of all start with finding the position vector for OA, because here we only have A, we don't have B. So OA, how are we going to get OA? Now look at this. This A is the position vector that we are looking for, corresponding to this formula here. And what does the formula say? We are taking N, so OA will basically be equal to, clearly look at OA. OA will be equal to 1/4 P plus 3/4 of Q. And what does this give? This is 1/4. What is the value of P? Clearly, so the value of P is 6, 2 minus 4. We just followed this formula here. It says N over M plus N. So our N is 1/3 plus 1, which is 4. And then here M, which is 3/3 plus 1. If you look at this again, this says if the point X divides a given, so our X here is A in this particular question, divides a given line AB internally in the ratio M to N. So here we're having our A dividing this in the ratio 3:1. So our M is clearly 3 and our N is clearly 1. Then X is the position vector of X. So the position vector is given by that formula here. So if M corresponds to 3 and N corresponds to 1, then this is what we are going to have. So 1/4 of this plus 3/4 of Q. And what is Q? Q is 10, 10, 8. So evaluating this, what do we get? So this will give us 1/4, 6, that is 1.5. Then this will give us 0.5. Then this will give us -1. Plus, on this other side, we have 7.5, 7.5, and then 6. So adding this up, this will give us 985. Okay. 985. Now let's take up another example. We're being told B divides PQ externally in the ratio 3:1. So let's have a rough sketch for that. If B is dividing PQ externally, so we will have our P somewhere here, we will have our Q somewhere here, and we will have our B somewhere here because it's dividing it externally. Okay, so this is our position vector P, position vector Q, and then position vector B. Let's call this our origin. So what is OB? What is OB? What is the position vector OB? So OB, clearly we can see PB to BQ is in the ratio PB. So how many units, as we were told? 3. In the ratio 3 to -1, clearly it's externally. So in the ratio 3 to -1. So PB will be going 3 units. So let's assume this is 2, 1. Then PB, we have it 3 units, 1, 2, 3. And then BQ BQ, we have that as -1. So we've clearly represented this. So this is 3 to -1. Now, what is going to be our OB? So the position vector OB will be given by, if you follow the formula, we will have -n over 3 plus -n of P. And what is our P? So we'll write that later. And then plus 3 over 3 plus -1 of Q. Okay, let's replace the values of Q and P. So here are the values of P and Q. So replacing that, this will just give us OB is equal to -1 over, this is 2. The values of P are 6, 2 minus 4, plus 3 over 2. The values of Q are 10, 10, and 8. If you evaluate this correctly, this is going to give us, so let's do it over here. So we'll have this, this gives, simplifies to that, this simplifies to -1, this simplifies to 2, plus this simplifies to, okay, so times 2, that will be 15. And then 3 over 2 times 10, that will also be 15 again. 3 over 2 times 8, so 2 to 4, that will be 12. Okay, adding this all up, this will give us 15 minus, that will be 12. This will be 14, and then this will also be 14. So that's basically how we go about the ratio theorem. That's basically how we go about the ratio theorem. Now, another thing we have is called resolution. So the next thing we look at is resolution of vectors. Now, a vector can be resolved, resolution of vectors. Now, a vector can be resolved into its horizontal and the vertical components. Now, the horizontal components, let's say this is what you have. This is your angle theta. So we have this as F sine theta. We have this as F cos theta. Now, resolving a vector into its horizontal components, we basically get the, resolving a vector, we basically get the horizontal components of that vector and the vertical components of that vector. So the horizontal components are basically just given by, as you can see, F cos theta, and the vertical components are given by F sine theta. Okay, fine. So that's how we go about it. Let's just say we have like F1, F2. So we have all these vectors here. How exactly do we go about resolving them? So let's say we have, this is our vertical, this is our horizontal. So we have F1, we have F2. So let's say we have F1, let's say we have F2. And you like to resolve them. So basically, if we are to resolve this into their horizontal, so this is F2, they will both have, so our horizontal component will basically be given by, horizontal component is given by F cos theta. But now we have F1 cos theta 1 plus F2 cos theta 2, because we no longer just have one vector, we have two. And the vertical component will be given by F2 sine theta 1 plus, sorry, F1 sine theta 1 plus F2 sine theta 2. Okay, now after resolving, we get the magnitude and the angle of the resultant vector. Magnitude of resultant vector. Now the magnitude of the resultant vector is given by h squared plus v squared square root. That is basically horizontal component squared plus vertical component squared, and then you get the square root. And the angle or direction, angle, or also called direction of resultant vector, direction of resultant vector is given by theta, which is equal to tan inverse of v over h. Okay, let's take up an example and see how this goes about. So let's say we are told, calculate the resultant, of v1 minus v2 plus v3. These are three vectors where v1 is equal to 22 units, 140 degrees. v2 is equal to 40 units at 190 degrees. And finally, v3 is equal to 15. So is equal to 15 units at 290 degrees. Now the resultant vector, we will start by getting the horizontal components. So the horizontal components will be given by, so we have v1 minus v2 plus v2. So v1 is 22 cos of 140 degrees minus v2. v2 is 40 cos of 190 degrees plus v3, which is 15 cos of 290 degrees. That's basically it. That's how you get the horizontal component of this. And then the vertical component, v, is given by 22 sine of 140 degrees minus 40 sine of 190 degrees plus 15 sine of 290 degrees. Okay, so evaluating all that in the calculator, we will be able to get that the horizontal component is equal to 27.67 units. And the vertical component will give us 6.99 units. So now for the magnitude and direction of the resultant vector, magnitude will be given by h squared plus v squared square root, which is basically our h squared 27.67 square plus 6.99 square root. And then the direction, or our angle theta, which is tan inverse of v over h, will basically be tan inverse of 6.99 over 27.67. So that's it. And this gives us 14.18 degrees. That's how we resolve a vector into its horizontal and vertical components. Let's take up another example. Let's say we are given vector. So let's say we are given vector A, example number 2, vector A1 is equal to 1.5 meters per second squared at 90 degrees, and A2 is equal to 2.6 meters per second squared at 145 degrees. They are acting at a point. So find the resultant. Find the resultant A1 plus A2. Now, well, let's resolve. The horizontal component will be given by 1.5 cos of 90 degrees plus 2.6 cos of 145 degrees. And the vertical component in a similar manner will be given by 1.5 sine of 90 degrees plus 2.6 sine of 145 degrees. And what does this translate to? So if you evaluate the vertical component, you will get 2.99. For the horizontal component, you'll get minus 2.13. So we can be able to get the magnitude of the resultant vector. So the magnitude of the resultant vector will be h squared plus v squared square root. And this will give us minus 2.13 squared plus 2.99 squared square root. Okay, so this basically translates to, if you do this, then you will get 3.67 meters per second squared. Okay, and similarly, we get theta, which is tan inverse of v over h. So this is tan inverse of 2.99 over minus 2.13. If we evaluate this, we will get this as minus 54.53 degrees. Okay, and clearly, as we can see, this angle right here was lying in the third quadrant. You see, this is the value of y, this is the value of x. So if you look at this x, y, so your x is negative on this side, your y is positive. So it's obviously on the second quadrant. So representing this on the second quadrant, this will obviously be 180 minus 54.53 degrees, and the angle is 125.47 degrees in the second quadrant. And that's how we resolve vectors into their horizontal and vertical components and find the resultant magnitude and direction.